Hello, one. So we have another MATHCOUNTS problem. So this was on the state test, on the number 30 on the sprint test. So Hank builds an increasing sequence of positive integers as follow. The first integer is 1, the second is 2, and each subsequent one is the smallest positive integer that cannot be form a arithmetic sequence with any of the previous terms. Okay, and the first 5 is given 1, 2, 4, 5, 10, and we want to know how many of the first 729 positive integer will be in that sequence. So like first, like it is not clear at first before we explore a bit. So which is why I'll just try whatever we can until we see the pattern. So like I just list the first 40 numbers to see if we actually need that many. But one thing is we know like this is one of the interesting numbers because this is a number that we see as power of 2s and 3s. This is like 3 to the 6th power. So which we need to remember power of 3s and 2s and stuff. So, and also like this is also a perfect square. So you can write like even exponent with something to the 2nd power. So let's keep those in mind. So like we are given 1 does work because, you know, I cannot make a sequence with 2 numbers. 1 and 2 should be in our list anyway. But the 3 doesn't work because if you try 1, 2, 3, that's going to be the arithmetic sequence, so which is no good. And then 4 should be in our list because we cannot combine 1, 2, and 4 to make a sequence, arithmetic sequence, so no good. It is actually good, like no good, so it should be in our list. So 5 is gonna be also because we cannot make arithmetic sequence with any of the previous number that we have. So 6, no, because 2, 4, and 6 will be a arithmetic sequence. And I can kind of try my best to list more, but so next one, maybe like I can do 1, 4, 7, so 7 is no good. 8, I can do like 2, 5, 8, so no good. And then 9, I can do like 1, 5, 9, so no good. 10 would be a number that we cannot make a sequence. Like for example, if we try with 5, because that's the small, like the largest one that is smaller than that. So 5 different. So if you go 5 more, so you get 0, so no good. So then 5 was like on our list. So the 11 is also in our list. We cannot make any sequence with 11 with any previous 2 terms. But 12 is no good because 10, 11 is. So if you combine with 12, so that will be 3 consecutive terms. And the 13 is the next one that we need to look into. So which is actually in our list because we cannot combine with any of the other 2 terms, previous terms, and same with 14. So I cannot do anything with 14 either. So how about 15? So 15 is obvious. I think 5, 10, 15, so no good. And 16 is, I can go with like 14, that means 12, but 12 is not list. If I go with 13 and 16, that's 3 less. 3 less will be 10, so this is no good as well. And then maybe next one is 17, so we can try like 14, 17, and 11, so that is a sequence. And then for 18, that doesn't look because 10, 14, and 18 does also give us a sequence. And 19, let's see. So for 19, we can probably try 19 and let's say 10. That's 9 difference. 9 less will be 1, so that means this is no good either. And then 20, I can do like, I guess 2, 11, and 20, so that is no good either. Okay, so you can keep trying this. Like, let me do a few more. So 21, I can just cross as well because 4 and 13 and 21 makes a sequence. And then similarly, like 22, I can do like 4 and 13. 22, let me see actually. So 21 I said 4, 13, so let me actually write that. So 4, 13, and then 21, right? So the difference was 8, so the difference is, if I subtract like that's 12, so that doesn't work, so that should be 5. So 21 with this doesn't work, but I think I can do 4, 13, which is, you know, 9 more, so 9 more will be 21 actually. No, 22. So 22 is cross for sure, but 21, so can we make 21? So like if I try, let's say 21, so 21 with the previous smallest is 7, so I can go, I mean 14, so 7 is not in our list, so 7 doesn't work. If I go with 13, so 21 to 13 is like 8, so if I subtract 8 from this, that should be 5, so which means I can actually do it with 5. So that means 5, 13, and 21 is a sequence. Like if you keep trying these, like you can get like 23, I'm going to leave that for you to find, and 24, and even 25, 26, 27, but 28 is not achievable. So that's one number we do not have a sequence with the previous terms. Okay, so now what? Like we kind of list a bit, like 29, we also can actually have 29. Let's say, because we skip a lot of numbers in this list, so which is actually easier to deal with. If I go with 14, for example, 14 and 29, that's difference of 15. So if you go 15 less, so you don't have anything, so 29 should be in our list. And then, but 30 is not, so because these 3 will make a sequence. So let's see what's happening, at least so far. So like we have 1, we have 2, we have 4, we have 5, like we have 10, we have 11, 13, like 14, and then 28, and 29. So we can increase more if you need to. So like one thing I realized, like you can try finding difference of these numbers and see if that's something gonna give us something. Usually like finding patterns of the given list is a good thing to try, but apparently it doesn't look like we have common difference. So, but another thing we can say, like all these numbers, like 29 is like 1 lower than a multiple of 3, and then this is 1 more than a multiple of 3. This is 1 lower than multiple of 3. This is 1 higher than multiple of 3. and this is like 1 lower than multiple of 3. So it looks like we have the same kind of everything, right? So this is like 1 more than a multiple of like 3 as well, because 0 plus 1. So it has that somehow relation, which is interesting. But at the same time, when you have something like multiple of 3s, which is a kind of reminder to think of as maybe base 3. So if I convert these into base 3, so let's see what we have. So this is going to be 1 still. So, and then this will be 2, and then that will be like 11, and then that should be like 12, and that will be 101, and then that should be like 1 more, which is 102. So, and then you get 111, and then this is like 1 more, 112, and then this would be just 1001. Like these are all base 3 numbers. So if you need some refresher on the basis, so you may do that. But this is our base changes, right? And then 29 is like 1 more than this, so which is like 1002. To quick check, like if you want to convert into base 10, so 1, let's say 3, right, 2, right? So that will be, so let me write that. So 112 in base 3 is equal to 1 times, this is the 3's place, this is 3 to the first, second, third, so 3 squared, 3 third, 3 to the third power. And then 0 times the other 2 doesn't make anything contribute. So you will get 2 times 3 to the 0 power, which is 27 plus 2, which is 29. So which is 29. Okay, so now we have a bit. Like now what? Like we have the numbers in base 3, but we don't really have much stuff still. But one thing we can say, like let's check the numbers in the digit in the base 3s. So we have like 1002, like 1001. But when you look at the last digit, this is 2, 1, 2, 1, like 2, 1, 2, 1, 2, 1. Like it's interesting pattern. So we just have only 1 and 2s on the last digit, which is cycling with those 2, which is interesting. And for the other one, this is like 100. This is 100. This is 11. This is 11. This is 10. This is 1. But I may add 10 to the left of this 101, and then I can make this like 01 as well. And then this might be 00. This might be 00 for the other 2 digits if I add those zeros, which is like the last digit always is 2s or 1s, but the other 2 digit or other like left digits is just 0s 1, which is also like interesting. So what we can do, maybe, we said this was a perfect square as well. So maybe we can compare these numbers in base 2 somehow. But one thing we can, like we don't want in base 2 is the 2s, right? We just need 0s and 1s, so in binary. Maybe we can subtract 1 from each one of these numbers. If I subtract, so you will get 0, right? So again, we are still base 3, but I'm just subtracting 1 from each one of these numbers. And then that will be 1, and then that will be 1, 0, and then this will be 1, 1, and then that will be 1, 0, 0, and then that will be 1, 0, 1, 1, 1, 0, and then that will be 1, 1, 1, right? And then that will be 1, 0, 0, 0, and then that will be 1, 0, 0, 1. Okay, so now we have all the digit in the new list as just 0s and 1s, which is like the binary digits. So like, but when you look at these numbers in binary, we have, this is like 0, this is 1, if you convert all these into base 2. This is going to be 2, because that's the 1 and 0, and then this is going to be 3, that will be like 4, and then this will be 5, and then this will be 6. It will actually continue consecutively, right? So that's going to be 8, because that's 2 cubed, and that will be 9. So meaning that, like when I know the number of lists right here, that's going to be increasing by 1. So which is cool as well, because we can just say like, we do have only, like when you look at the list right here, so we have the digits 0, like 1 and 2s, right? And 0s right here. But when you subtract 1, so you're using only 0 and 1, which is only 2 option. And then when you look at these digits, like in base 2, you actually consecutively add each numbers, right? So meaning that if I know how many numbers I can write in base 2, then that's actually going to be number of terms in entire list, because this is actually the perfect square. So like, which is 3 to the 6 power. So every time, like we do have 2 options for the digit. Like for example, if I want to think of this, like first thing we need to realize actually is we are going to get this number at most, right? Which is going to be 10000000 base 3, which is a 7-digit number. But when we subtract 1 from these numbers, you actually end up getting 6 digits. So this will be like 2, 2, 2, 2, 2, 2s, like whatever numbers you get when you subtract 1. So that means that will be 6 digits at the end for 729. So you will get like you will get the number like 6 digit or lesser. So which means every one of these digits, so you have 2 options. So when you write in this way, which is 0s and 1s, you're going to add it. So which is going to be unique number when you choose those, like when you choose the 1s and like 0s. So for example, think about this way: 1, 2, 3, 4, 5, 6, and then you're trying to make this a number. So if I choose this is 0, like this is 0, this is 1, this is 0, this is 0, this is 1. So this is one of the numbers. What is this number will be? Like that will be just equal to 1, 0, 0, 0, 1 in base 3. So 0, 1, 2, 3, 4. So 3 to the 4th, 81. So that should be 82 in base 10. So, but if I want to make all of these zeros, for example, like 0, 0, 0, 0, 0, 1, and then if I want to write this, that will be just 1. So which is our first list, meaning that like I can add a bunch of zeros to the left. So it depends on the value I choose for this digit. So either 0 or 1, I will just get a unique number from my list. So which is why the number of like integer in this list is actually a number of ways to actually make this a 6-digit number in base 3 just using ones and zeros, which means every digit have 2 chances of being chosen. So either 0 or 1. So which is why we have 2 to the 6 power, which is going to be 64. So that is the kind of one way to think of. That is going to be number of terms. If you're not convinced, you can just like, I know, list a few more and then kind of see if that's really the case. And you can just always convert and see if this pattern will continue. But this is the pattern approach. It doesn't really prove anything, but it is solid to say that that would be your answer. So I'm going to kind of leave the actual proof of why this actually works for you as a challenge. But another way to look at this one is maybe looking at the pattern slightly differently. For example, if I look at the first 3 numbers, right? So 2 of those 3 does work, right? So the first 2 of the first 3, so 2 out of 3. And then if I look at the first 9 numbers, like because 9 is 3 squared, for 9 numbers, we have 1, 2, 3, 4. So 4 out of 9 numbers does work. Then if you want to look at the first 27 numbers, which you can see this is 3 cubes. So, and then previous one, we have 8 of these actually working, 8 out of 27. And then this is the power of 2s, the first ones, like 2s to the first power, 2 to the second, 3 to the third, and this is 3 to the first, second, and third. So, and then if you just keep doing this, so then the last one will be 2 to the 6 and 3 to the 6, because that's 720, like 9. So that's going to be 64 of these. 729 numbers should work as well. So you can kind of go with as well. Anyway, so that was interesting problem. So at first, it has nothing to do with the base system when you read the problem, but when you start exploring, sometimes you need to think of number 3 as well. So that was what we did in this problem. Anyway, I'll see you in the next video.